important thing, last but not least, Professor Dan also have a brief years, a couple of years, working as the visiting professor here. Many years ago, like 40 years, 50 years ago, and then 70. I mean, FYI, it's just really, to be honest, it's just before my existence in this earth as well, like 50 years ago, and now, Professor Nancy being our special guest for the science faculty anniversary 55 years. All right. Also, welcome Professor McCammon. All right.
Okay, so I'm now at the University of Wisconsin-Madison, and I do X-ray astronomy. And how many of you know what X-ray astronomy is? That's fine, because today I'm going to start out by just showing you some X-ray astronomy while we're doing it, because I'm here because I was just in Australia for 6 weeks with my graduate students and my postdoc, and we were flying a X-ray astronomy telescope that they built. So after that, I'll talk about what X-ray astronomy is and why we do it. And then at the end, I'm going to talk a little bit about the future of X-ray astronomy and why it's going to be important for understanding the universe we live in. Okay, so I'm going to show you what we were doing in Australia. We were up here, way up in the corner, and this is a very remote area. Just to give you, I show you some of the surroundings there so you can see. This is the main road to the launch site, and the side roads are even worse. But this is the launch site where there is a private Australian company that is building a spaceport there. So they cleared off the jungle for this area, and we were their first customer. So our rocket was the first rocket launch from Northern Territories ever. This white building here, that's the shelter over the launcher, and this is the place where we stay to when we launch the rocket. So that's the closest the people can be. But around there, it's very nice. We're very close to the ocean, and there are hundreds of kilometers of beautiful beach like this, even nicer than Had Samila. But as you see, this is Sunday afternoon, and how many people do you see? All these beaches are completely deserted, no people. Here's why. Because there are these crocodiles. They're very big, and they're very fast, and they love people. And they can also swim up the rivers, so you can't go into the rivers either. This is one, he's eyeing this ibis here for breakfast. Okay, but back at work at the launch site, these are my graduate student, two of my graduate students, getting our experiment ready. So the X-ray telescope is in here, and the electronics are up here. And then we put that together with the parts that NASA provides. These are things that everyone who flies these small rockets wants to use. So up here in the nose cone, there's a parachute. And then we have radio transmitters to send the signals to the ground. And then below that is our experiment. So you take this out, and that's that whole payload, and now it's on top of the rocket motors. This is the main stage and a booster here. And then you wait until it's nighttime for the same reason you look at stars at night, because the sun makes a lot of X-rays that scatter off the atmosphere. make the sky bright. So we launch at night. And
5, 4, 3, 2, 1, 0.
try again.
5, 4, 3, 2, 1, 0.
Okay. ไม่เป็นไรครับ Okay. So but not now. Okay. So here is us in this launch control center watching the data come down on the radio, and you can see it looks like we can see everything is working right. So everyone is very happy because we worked for 4 years to get ready for this, and now only have 5 minutes to get data, and it is all good. So this is my group at Wisconsin. So there's me and 2 graduate students and 1 scientist and about 7 undergraduate students that work on this. So now we have to get back. What is X-ray astronomy? Okay, well, first, what is an X-ray? Well, X-ray is a kind of light, okay? So actually, all kinds of light are the same thing. They're what we call electromagnetic radiation, electromagnetic waves, and we give them different names because they come from different kinds of things that if you change the wavelength. At very long wavelengths, we call it radio waves. And shorter ones, we call it infrared. Shorter yet is visible light. And then you go to ultraviolet and X-rays and finally gamma rays. But it's all the same thing, just the name is different. But different kinds of things make it. Very cold things, you know, minus 200 degrees, they can still make radio waves. Visible light takes temperatures around 5,000 or 10,000 degrees. So this is the surface temperature of most stars, is around 5,000 to 10,000 degrees. So stars make all their light invisible. The hottest stars make ultraviolet light, but to make X-rays, you need gas that is 1,000,000 degrees. So stars don't make many X-rays, but there are other things that do, as we'll see. But then if you want to look at these things that come from the sky, you have to worry about how far they will go in air. And so this is the atmosphere here, top of the atmosphere down to the ground. And this is the wavelength here. So in the radio, that can go all the way to the ground. So you can do radio astronomy from the ground. I think you have a radio telescope here, yes? Yes, okay. Visible light, and actually what your eye can see is only wavelengths from here to here, very small amount of the spectrum. But there also, the atmosphere is very transparent and visible light can get all the way to the ground, so you can do optical astronomy from the ground also. But when you get to X-rays, they'll only go about this far in air. So you have to get above almost all of the atmosphere. So in order to do X-ray astronomy, you have to build a telescope and then fly it on a rocket to go above the atmosphere, or on a satellite. But those experiments are expensive and take a long time. So the question is, since X-ray astronomy is hard to do and expensive, why bother? So I try to lead you through why it's very interesting. So first, I want to show you a galaxy. This is a galaxy that we think is very much like our own Milky Way galaxy, except since we're inside of ours, you can't see it like this. It's very hard to see what ours looks like. But we think it looks a lot like this. And the Earth and Sun would be here about halfway from the center to the outside edge. So our only view of our galaxy is from here, and we can look in towards the center, we can look out towards the near edge. If we saw this on edge, it's a very thin disk. And so we can look up and down the thin way also. And so this is what you see from here. This is everything in the sky that's optical sky that's bright enough to see at night. So this is all things you could see with the naked eye. If you were someplace it's very dark and clear, and you could see the whole sky at once. But the way this map is made is this is looking in towards the center of the galaxy, and this is going around in the disk, and this is looking out towards the near edge. Okay? And then this is looking up and down the thin way. So if you look the thin way, you soon run out of stars. But the stars you do see are relatively close and bright. So you see small number of bright stars up here. If you look in the disk, you can see stars very far away, and so they are faint and they all blend together into this Milky Way. So along here, we have a Milky Way. So the important thing though is everything on here is a star. If you have a telescope, you can also see other galaxies, but the bright things are all in our galaxy, and they are all stars. Now, if you look at the X-ray sky with an X-ray telescope, this is what it looks like. Okay, it's very different. This is the 55,000 brightest X-ray sources. There are no stars in this picture. Stars make some X-rays, but not bright enough to show up here. So 90% of these 55,000 sources are supermassive black holes. Each one is in the center of its own galaxy, and these are not even very nearby galaxies. These are galaxies at Z of 1 to 2, which means the universe was a half to 1/3 as old as it is now when these X-rays started out to come here. You do seem to see some sign of the galaxy, not so much here, but that's because gas between the stars in our galaxy absorbs the X-rays, so you cannot see the fainter ones here. And then the other 10%, mostly these blue things here, are neutron stars and stellar mass black holes in our galaxy that have things falling into them that gets hot and makes a lot of X-rays. So neutron stars are stars that weigh a little bit more than the sun, but they're only the size of Hadyai. They are about 10 kilometers across. So they are very unusual things themselves. There's also, our galaxy also has a supermassive black hole. We think most of them do. Right in the middle of the galaxy, there is a black hole that weighs 4 million times as much as the sun. But you can see it does not show up here at all, even though it's very close. And this is because there's nothing falling into it. These bright ones we call quasars, and they have stars getting pulled apart, and that gas falls in, and because the gravity is very strong, it rubs together and gets very hot, like 10 million degrees. And then it makes a huge amount of X-rays. The X-rays are 100,000 times brighter than all the stars in the galaxy put together. So you can see these galaxies very far away. We call them quasars. Our galaxy also has a black hole, but right now it seems there's nothing falling into it. It has already cleaned out all the area around. But there is evidence that millions of years ago, it had the stuff falling into it, and it might have been a quasar also. Okay, so what else can you see in the X-rays? This is an X-ray picture of a star that exploded about 400 years ago. And this is a big ball of million-degree gas. It's made with the Chandra X-ray telescope. And in these X-rays, by looking at the color of the X-ray, these colors, of course, are made up because your eye can't see X-rays, but these are different wavelengths of X-rays, and they show that there are different elements there. There's iron and carbon and silicon, all these heavy elements that the universe started out, it didn't have anything except hydrogen and helium. So all of the carbon and iron and stuff that we're made out of, that the Earth is made out of, was once down inside a star. And we understand how the star fuses helium together. That's what makes the energy to light it up. But we don't understand so well how it gets out of the star and across the galaxy to make a new solar system like ours that has planets and people. So this is what we're studying. And this, we think, is the first step, that the star explodes and the insides of it get thrown out as hot gas. But we don't, right now, can't see how that travels from one part of the galaxy to another. And this, by the way, is where neutron stars come from. This little white dot in the center is a neutron star. That was all that's left of this star. It started out weighing about 25 times as much as the sun. Most of that is out here. There's about 1.5 times the mass of the sun left in that neutron star, which is only 10 kilometers across. Okay, but my group is more interested in diffuse hot gas, the gas that's floating around between the stars. Some of that is very hot, 1 million to 3 million degrees. This is a map we made of the whole sky with a German satellite in 1990. And the red is brighter and the blue is cooler, but this is showing the amount of hot gas. And there's this ball of very bright hot gas. There's a lot here around the center of the galaxy. And we want to look at that, study that, to try to figure out where it comes from. So we want to see what elements are in it, because different kinds of stars, when they explode, make different amounts of different elements. So one young star supernovae make a lot of oxygen and not too much iron. Old stars that blow up make a lot more iron. So you can look at the ratio of iron to oxygen and get an idea what made it. So this was our target. It's a little bit too far south to see from North America, so that's why we have to wait until NASA has this expedition to Australia. If we can look at it, the X-rays come out in the characteristic lines of different elements. So this is the color of the X-ray across here. This is what we call a spectrum. This is the color or the energy of the X-ray, and this is how bright it is. So we look at individual photons of X-rays, and if they come at this energy, we know they come from oxygen with 1 electron left around it. Oxygen normally has 8 electrons, but in the hot gas, most of them get knocked off. This line here is from oxygen with 2 electrons. This is from neon, from magnesium. So we can see all of these different elements. The problem is that it's hard to measure the energy of the X-ray so accurately, the color. This is a very accurate measurement, but the Chandra Space Telescope, which is NASA's flagship X-ray telescope, it would make a spectrum like this because it can't measure very accurately, so it smears out the spectrum. And so you can see, oh yes, there must be a lot of oxygen there, and must be some magnesium, but you cannot see all the detail. So that's what we have been working on, is how to make a different kind of X-ray detector that can measure the energy more accurately. So our kind of detector the idea is very simple. We do what's called thermal calorimetry on individual photon. Just like the biologist will, or the food science people will measure how much energy is in the food. They put it inside something, put some oxygen, they burn it all up, and they see how hot it gets. And that tells them the amount of energy. Well, we do that with single photons. So calorimeter is very simple. You have something that will stop the X-ray and change all the energy into heat. And then you have a thermometer that measures how much the temperature will go up. So by how much the temperature goes up, you can tell what the energy of the X-ray is. This is the heat capacity of the bucket of water, and that's the energy of the X-ray, and that tells us what delta T should be. And then there's a weak thermal link to cool it off, so it will cool off and you can wait for the next X-ray. The detectors we make, this takes about 1 millisecond to cool off. But of course, to actually get the detectors to work takes a couple of years of graduate student time. So this is one of the former graduate students. And these detectors, in order to see the very small amount of energy that's in an X-ray photon, you have to cool them down to a 20th of a degree above absolute zero. So this is a refrigerator that will get that cold. She's putting liquid helium into it. And the undergraduates also help us develop the detectors, and they have fun. This was making Helmholtz coils to cancel the Earth's magnetic field. And so we end up making these detectors. There's a microfabrication lab in the engineering campus, and we use that to make these. This was the first one we make. This is the one we just flew in Australia. You can see it is much more beautiful than the old one, but more important is it's bigger, so we can collect more X-rays. So this whole detector chip here, this is a silicon chip. It's about 3 centimeters across. But there's this problem. 0.05 Kelvin, 50 millikelvin is quite cold. It's never been that cold in space. Space is 2.7 Kelvin is the coldest you can get there. So we need a refrigerator, even up in space. But I have, fortunately, a very smart graduate student who taught herself how to do mechanical engineering and thermal design. And so she designed this refrigerator that will cool to 50 millikelvin. That's not so hard, but it will stay cold through a rocket launch. That was hard. So she figured out how to do that. We use something called adiabatic demagnetization. This is one of the undergraduates getting it ready to fly. And so then you put that refrigerator inside this aluminum cylinder that's the rocket skin. And you put it on top of the rocket. This now is out in New Mexico, White Sands. This is where we fly most of our rockets if we don't need to go to the south. So this is in the blockhouse. This, one of the graduate students then, and this is the control box that can control the refrigerator from the blockhouse over wires that go out to the launcher. And this is the launcher there, very much like the one we used in Australia. So it starts out horizontal, raises up to vertical. And here's the payload again. Our experiment is here. And this is the main rocket motor. It's called the Black Grant. And this is the booster.
3, 2, 1, rocket.
So this is the way that the rocket works. You shoot it pretty much straight up. It does not go into orbit. That takes a much bigger and more expensive rocket. So this kind we can get easily because it costs about 1% of what even the smallest satellite that NASA flies is. So first stage burns for 3 seconds and falls away. Then you light the second stage, and it burns out at about 20 kilometers altitude. That's about the height the Concorde used to fly, so not all that high. And from then on, you are just coasting. But you are also going 8,000 kilometers an hour straight up. So it will coast on up to about 250 or 300 kilometers and then fall down again. And that gives you about 5 minutes above the atmosphere to look around. So that's all the observing time we get is 5 minutes. And then it falls down, and then at about 6 kilometers, it's slowed down enough from the air friction that you can open a parachute. So the next morning, you send the graduate students out to look for the experiment. And they get to ride around in a helicopter to look for the parachute, big orange parachute on the sand. This is the white sands of New Mexico. And you can see they're very happy. They found it in good shape. So they will load it in the helicopter and take it back. Okay, now I can show you something that no one else has seen yet. Oh, sorry, no, that comes later. No, it's here. Okay. So these are the first result from our Australia flight. You're the first ones to see them. This is not the final data because it will take the graduate students probably another 6 months to figure out the best way to analyze the data. And so in the end, we will get better energy resolution, so the lines will get narrower, and we will get more accounts out, less dead time. But this already looks very good. That's why everyone was so happy in the blockhouse. So we can see lines here from iron, silicon, carbon, nitrogen, oxygen, more iron, magnesium, neon. So this will be very happy. We can measure relative amounts of all these things and figure out a lot about the hot gas. Okay, so what's the future of X-ray astronomy? Well, we think it is important to the big picture of how the universe works. Probably most of you have seen this. 40 years ago, when I was a student, we thought everything in the universe is ordinary matter. And the big problem in astronomy was to figure out how much is there. If you have only a little bit like this, then the universe is open and will expand forever, was the idea. If you have just this much, that's what we call the critical density. 100% on this circle is 100% of the critical density, which is where the expansion, since the gravity of the matter tends to pull it back together, why it should stop after an infinite length of time. And if you have more matter than that, it will stop the expansion and then contract again, which is what a lot of people wanted at the time. But however, what we could find was only about 2% of that. Remember, all the stars and everything are a very small fraction. So everybody wondered, well, where is the rest of the matter? And now we know that of all the matter in the universe, ordinary matter is only about 20%. Most of the matter in the universe is something we can now call dark matter. No one knows what it is. It's some kind of a particle. The mass of that particle is uncertain by 30 orders of magnitude. And no one has any idea what it is. It's not in the standard model of particle physics. No one has seen it even in the big accelerator in Geneva. So it's something completely unknown. And the theorists who worked beyond the standard model, the particle theorists, had a good candidate for it. But that candidate you could detect with a big detector underground. And now people have looked very hard and they don't see it there. So it's something else and nobody knows. And even worse than that, 70% of the stuff in the universe isn't a particle at all, isn't matter. It's some weird form of dark energy. And again, the theorists have no idea what it is, but the only thing it changes is how fast the universe expands. So, and because there is so much dark energy, the expansion of the universe now isn't slowing down. This matter makes gravity that holds it together, but dark energy is very strange. It has the opposite. It's like negative gravity. So actually, that the universe is not slowing down. This is expansion. That's what people were, when I was a student, this was the main object of every big telescope, was to measure how fast the universe is slowing down, the expansion is slowing down, because that tells us how much matter there is. But now we know, in fact, there's this dark energy and the expansion rate is actually increasing. So the universe will definitely fly all apart. But nobody knows what this is. But the only way you can learn anything about it is to look at the history of the expansion. And so you must measure many objects far away. And one of the biggest things is looking at X-rays from clusters of galaxies, because they're bright and you can see them far away. But since I'm an observer, I worry most about, this is the only part you can see. So as an observer, I give you the observer-centric view. This is all there is. Of course, it's only 5% of everything in the universe, but it's 100% of what you can see. Now, if you go back and look at the cosmic microwave background, this is when we first were pretty sure there was a Big Bang, because this is what the universe looked like only 100,000 years after the Big Bang. It cools off just enough that the electrons can combine with the protons and make hydrogen atoms, and the universe suddenly becomes transparent. So we can see where all the matter was at that moment, all the normal matter. And you can add all up all that matter, and it comes out just the right amount, just this 5% that we think should be there. But these different colors here are density fluctuations. So these red parts are more dense and the blue parts less dense than average by a tiny amount. But anytime you have more dense in one place and less dense in another, you have stronger gravity here. So it collects more material, and these little fluctuations grow, and eventually they get dense enough they become galaxies and stars. So we thought that, okay, this is where the stars come from. These red spots are the things that will end up being clusters of galaxies and galaxies. So this is what the universe looks like now. And we used to think that it all came to here. But now that we can count all the galaxies and know how many stars are in each and how much mass that is, we can add up all this mass. And it's only that much. So we need, all this is something we can't see or didn't see at the time. Okay, but we got a big boost back in early days of X-ray astronomy. Okay, this is an optical picture made with a ground telescope of a cluster of galaxies. So each of these galaxies is about the same as our Milky Way galaxy, 100 billion stars. And now we know a couple of 100 billion planets in that. And there are about 1,000 of these galaxies in the cluster. And so they are all together. But they pointed, we knew that our galaxy has about 200 neutron stars and small black holes in it that are X-ray sources. So we think when they first launched this satellite that has an X-ray telescope, they think, we pointed at the cluster of galaxies. You put together the light from the 200 neutron stars, and you should be able to see X-rays from each of these galaxies. But instead, this is what they saw. Okay? So you can see the individual galaxies. But the thing that really knocks your eyes out is there's this huge ball of 100 million degree gas in the middle of the cluster. All the galaxies in the cluster around this. But it's easy to calculate how much mass is in this hot gas and the temperature. So the temperature is 100 million degrees. The mass is about 8 times more than the mass of all the galaxies in the cluster put together. So most of the mass in the cluster is in this hot gas. Actually, there's even 3 times more mass than that, because even this hot gas has a high pressure, and you must contain it somehow. It's not inside a glass bottle, so the only thing that contains it is gravity. And you can calculate most of the mass is in the hot gas, so you think its own gravity holds it together, like the sun is held together by its gravity. But you can calculate you're a factor of 3 short. You don't have enough, this stuff should just spread out. So that tells us for sure there is dark matter in there too. But just the mass of the hot gas, okay, adds a lot. So this is everything we could see before. Now that we can see the hot gas in clusters, we can see this much more of, this is the whole universe in normal matter. And now we can see about half of it. So the question is, where is the other half? Okay, well, we don't see it yet, but the theorists have an idea. This is a map, a theorist map of the dark matter in the universe. So the green, and they think it's all drawn by gravity into these filaments, and where the filaments come together, you can see the density is the color, and you can see these little red spots. And those are where the density is high enough that the gas can cool and contract more and form galaxies and clusters of galaxies. So all this stuff that we can see is at those little red spots. But they say, well, about half of this gas is still out in these green filaments. And it's heated to about 1,000,000 degrees from falling in. The normal matter there is at 1,000,000 degrees because it fell into the gravitational potential well of these filaments. So at 1,000,000 degrees, the hydrogen helium have lost all their electrons, and that makes it very hard to see. So the only way you can see this now is from the X-ray emission. But because the density is low, the X-rays are very faint. So we will have to build better detectors and a very big X-ray telescope on a satellite in order to see this. But when we can see it, then hopefully we'll find a lot of this missing matter here. The current idea from the theorists, again, is that more than half of all the normal matter in the universe is in the form of diffuse hot gas. And the only way you can see that gas is in the X-rays. So that's why I think the future of X-ray astronomy will be important for figuring out what the universe we live in is like. So I hope you enjoyed this introduction to X-ray astronomy. Good to see you all. And we have lots of time for questions.
All right, thank you so much. And you can ask in Thai, I do translation, or just ask directly in English.
Yes,
I have a couple of questions.
Use the mic.
Okay. First question is on the technical part. From the data you have, how can you map the spatial information of it?
We do not have any spatial information.
Oh.
Our telescope is a hole that the detectors look out through.
Uh-huh.
So in order to get enough X-rays in 5 minutes, we must look at a big piece of the sky.
Yeah.
So we look at 60 degrees field of view, and we get the average over that. So we have to make models to fit the spatial distribution. If we have a big satellite that can look for a year, then we can have a telescope and get very good spatial information. Now the Chandra X-ray telescope has resolution of 1 arc-second, but it has very small field of view, so can't see too much. We actually, and the problem, of course, with Chandra is it has the old detectors that don't measure the energy accurately.
Sorry.
We helped build a telescope for a Japanese satellite that will have the new kind of detectors on it. And that one it's called CRISM, and that will get launched early next year. But it is designed especially for looking at black holes and neutron stars and things like that. So it also has a very small field of view. It can't do this kind of measurement. So we have to keep flying the rocket for a while. And in the lab, these detectors, well, let's see, to go back, the old-style detector, the energy resolution, how accurately you can measure the color, is limited to about 120 electron volts, smeared out by 120 electron volts at 6 keV. And this is very fundamental due to the statistics of ion formation, because this is a CCD, it counts how many electrons are reduced, but that has statistical fluctuations, so you can't do any better. These ones we're flying on the rocket have about 8 EV resolution. And we now have a better kind of thermometer that we're working on. So the detectors in the lab we have now, and we'll make into a new sounding rocket payload, have a 1 EV resolution. So we can measure even more accurately.
Yeah. Actually, my next question is a follow-up from that. How do you handle the Doppler effect or Doppler broadening of the hot gas or interstellar object that move away or closer to us?
Yeah, we can, at 8 EV, it's hard to measure radial velocity because 8 EV is about 500 kilometers per second. So we can't quite see rotation of the galaxy. We can see expansion of supernova remnant. That sometimes gets that fast. But with 1 EV, we can measure radial velocities usefully.
Thank you.
Any more questions? Please,
Thank you very much for your talks. Very entertaining. Actually, I always love astronomy. But I went to university and I stopped after Astro 102. So the math is too difficult for me. But I always read the story about dark matter and so on. Sometimes I imagine dark matter, could it just be like a mass like planet that is floating around, it exhibits gravitational force, but it's very difficult to detect. Is this possible? Or what's the difference between the dark matter and regular mass?
Most of the regular matter will interact with light, so you can see it. Okay. The dark matter has very little interaction, none at all with light. That's why it's dark. So you can't see it. The theorist's model for it, that was called a WIMP, weakly interacting massive particle, was supposed to be about 1,000 times heavier than a proton, and it would have a interaction cross-section. I think we lost the microphone here. Okay. It would have an interaction cross-section about like a neutrino. So people have built very large detectors and put them underground to try to see this. It's not there. So you need a different model. So it could be a particle that has no interaction at all except gravity, so we will never find it by direct detection. We also look for, maybe it is a particle that decays into something normal, like 2 gamma rays. So people look for gamma rays or positrons coming from space that they can't explain otherwise. And in fact, there is this excess of gamma rays from around the galactic center, but most people think there is a better explanation than decaying dark matter. That's called indirect detection. But if the dark matter particle is stable and does not decay into anything, and has no interaction cross-section except gravity, then we will never have any more information than we do now. But it's clearly there. Some of the best evidence is that hot gas in the cluster that we could easily count. That will fly apart in a few million years if it doesn't have dark matter in it to make more gravity and hold it together. The other one is the rotation of our galaxy. The sun goes around the center of the galaxy, and just like from the length of the year, you can tell the mass of the sun. Okay, that's just Newtonian mechanics. Same thing for the sun going around the center of the galaxy. You can tell how much mass is inside the orbit of the sun. It takes about 100 million years to go around. And from that, you know how much mass is inside. You count all the stars and add up all their mass and the gas inside. you only get about 1/3 of what you need. So there has to be dark matter also in our galaxy. So they think, well, maybe it is small black holes, or there are a lot of Jupiters out there floating around between the stars. But they do these surveys of what they call microlensing. You look for gravitational lensing, and you don't find, you can put upper limit of 10% of the dark matter can be something like that. So we think it has to be a particle of some kind, but no one has any idea what kind.
Thank you.
For the instrument to measure the spectrum of the X-rays, what kind of the elements or the parts that you or your group used to disperse the X-ray energy before detection the energy, to disperse the spectrum of the energy?
What kind of elements or what?
Yeah, what technology, what kind of, before we measure the spectrum, we need to disperse the X-ray into different energy, right? And then we detect it for energy for each wavelength or each energy.
Yeah.
So what kind of element we can
What
disperse?
kind of element is in the detector?
Right. For example, the spectrometer in the optics, we have a grating, or we have a prism in order to disperse the light spectrum. But for energy, what is that element for X-ray?
Well, this is one of the good things about the, we call them microcalorimeter detectors, is it doesn't matter much what you make it out of. If the ordinary detector, you must, what you want to do is, each photon knocks off some electrons, and a higher energy photon will knock off more electrons. So you want to, after one photon is absorbed, you want to collect all the electrons and count them. And even if you can collect them perfectly and count them exactly, you still have the problem that since only about 1/3 of the energy goes into making electrons, there's statistical fluctuation. But in order to get the electrons at all, you must make the detector out of something that the electrons move through easily. And there are only a few things. You can make it out of silicon or germanium, or more difficult, you can make it out of indium antimonide and gallium arsenide and a few other, only a few things. But for the calorimeter, all you need is something that will turn the energy into heat. It has to stop the photon and then turn the energy into heat. So it doesn't matter too much what it's made out of. Actually, semiconductors are not very good because they have metastable states that will store energy for a long time at low temperature. So the detectors that we are flying now use mercury telluride. It's a semi-metal, so you want something with a low heat capacity, low specific heat, but high Z so it stops the X-ray easily. So mercury telluride was the best. These new detectors have a much more sensitive thermometer, so we usually just use gold as the absorber. So they're made of gold. The ones now are made of mercury telluride. But you can make it of anything. And this is nice for some other experiments. Like, you know about neutrino-less double beta decay, that you can have a decay that has 2 electrons come out, but no neutrinos. So all the energy is in the 2 electrons. But you must catch both of them and not lose any energy, and then you get a sharp line at the energy you know. So people try to look for this, and they make but if you try to use external detectors, it's hard to catch both electrons before they lose any energy. So you make a calorimeter out of your element that you think has double beta decay, like tellurium-138 is maybe one of the best candidates. So now there's a group in Italy that has this experiment called Cuore, and they have 1,000 kilograms in 1 kilogram blocks, and they have 1 kilogram block of tellurium oxide, and it has a thermometer attached, and they look for the temperature to go up.
I see.
And because the decay happens inside the detector, you automatically get all the energy from both electrons. So they can get very low background.
Okay.
And so they actually have a ton of tellurium oxide in the dilution refrigerator in the Gran Sasso underground laboratory. But
Nice.
it makes it good for many laboratory experiments because you can make it out of anything.
Wow. Is that simple? Okay. Is that in the future maybe a big project like James Webb Space Telescope that we would have X-ray telescope out in the space to observe?
It doesn't need to be that big, okay? That is a $12 billion satellite, but it needs to be pretty big. We think maybe about $1 billion. So if NASA does it, it will be a long time to wait still. But well, it will need these next generation detectors like we're working on now. Actually, one of my former students who was professor at Purdue University for many years, but he got an offer from China to go back to China. So he gets a lot of support. But he went back to Tsinghua University largely because China has a very ambitious high-energy astrophysics program in X-ray astronomy. So he is trying to get a satellite like this made much sooner than NASA will do it. So I have been going, until COVID, I was going to China to help him set up his lab because he's trying to develop the same kind of detectors that we are. So we work together on that.
So in terms of possibility, in terms of technologies, it's possible then for the like X-ray James Webb telescope. I mean, the X-ray like James Webb telescope is possible in terms of technology.
Yes, I think we have the technology. The detectors need to be developed a little bit better so we can make them easily and uniform. We have single detectors now that are 1 EV, but we need to make them bigger and keep the energy resolution.
Physically bigger. You know.
Well, we must make each pixel needs to be bigger, but if you make it bigger, it has more heat capacity, so we have to work a little harder to get
Because
1 EV. And then we need a few thousand of these pixels in an array.
Because
Okay,
it's
and
going to
then
be the payload, which is, you know, it's supposed to be small as well when it be in the payloads of the satellite, right?
is the microphone on?
Oh, sorry. Yes, it's on. But when it's been a payload, but when the sky stuff have to be set up on the payload, so it have to be smaller as well, right? I mean, you have to concern about the size as well because it's on the payload of the satellite. Am I correct?
Okay, I'm not sure I understand the question. Can you say again?
All right. No. Okay. Just I'll ask you later about that thing. I have my very old question as well. Instead of launching the rocket and send your experiment using the rocket, can we use the something like the high altitude balloons, the HAB, instead of launching the rocket?
Well, the problem is that a very big balloon, a good balloon, will get you up to about 1 gram per square centimeter of atmosphere left. The X-rays are absorbed by about 100 micrograms. So the balloons don't go high enough by a lot. It would be nice because the balloons stay up for many days and you get a lot more than 5 minutes observing. And people do gamma ray astronomy because the gamma rays will come down lower. But X-ray astronomy, you have to have a rocket or a satellite.
And what the altitude that you need, actually?
The altitude we need is about 160 kilometers.
Oh, right. HAB cannot reach that because like 50, the world record of the HAB is going to be like 50 kilometers as far as concerned.
Yeah, I say it's about 1 gram per square centimeter, so it's way too much.
Makes sense. Cheers. Any more questions? All right. I think, is it? I think it's about the time now. Well, 1 minute to go. So thank you so much, Professor Dan. So I wish everyone enjoyed the talk and and got a lot more knowledge about things. All right. ครับ ท่านนี้นะครับเป็นแบบ QR code นี่นะครับต้องทุกท่านสแกนแล้วก็ช่วยประเมินครับ The sound just go to the online audience, but not in
Oh.
room audience.
Oh, I see. Before we